Bom dia a todos. Bem-vindos. Muito obrigado por estarem connosco neste seminário. Penso que só ainda temos portugueses connosco. A qualquer momento podem entrar espanhóis. De qualquer das formas, este é um seminário sobre desenvolvimento de formulações no que diz respeito à compressão e estudo das variáveis de compressão no sentido de melhorar depois o processo de fabrico. Têm à vossa disposição a possibilidade de colocar questões, as quais serão respondidas no final. Mudo agora para o inglês, porque a sessão vai ser conduzida em inglês. Good morning to all. This is a seminar regarding compaction analysis with the Gamlen series equipment, and this seminar will be conducted by Dr. Rebecca McVicker, who is the expert on the subject. So please, Rebecca, now it's up to you.
Hello everyone, I'm just going to make sure my presentation is full screen. So today I'm going to be talking to you about carrying out compaction analysis, specifically using our Gamlen D-series equipment. The Gamlen D-series can be used for other applications, say for making small batches of tablets, for other tests like stability testing or disintegration testing, or just simply to make small batches of tablets. But today I'm going to be focusing on using it for compaction analysis. So why do we want to carry out compaction analysis? Well, because we all want to make better tablets, the best tablets that we can. And the difficulty with this is that a very good tablet has to meet a lot of criteria. They have to be strong, porous, and free of defects. And the difficulty here is that a tablet that is very porous is not likely to be very strong. And if we don't have enough pores, then the tablet is going to take a long time to dissolve, and it's more likely to cap in production. If we want to avoid other defects, we need to make sure that the blend is well lubricated so that it doesn't stick. But in order to reach that level of lubrication, we'd have to make sure that we don't over lubricate the blend. If we over lubricate, then the particles within the tablet won't adhere to each other, and we end up with weak tablets. So we're always playing a balancing act between these different factors when we're carrying out tablet formulation. And ideally, we would want to know if we have hit all these targets before going into full-scale manufacture, and that's where compaction analysis comes in. So if you're not carrying out any kind of compaction analysis and you're trying to tell if your blend is going to make a good tablet, then it's likely that you're in some way trying to infer compaction behavior from other powder properties. And my background is as a material scientist, so this would have been what I was originally doing in that role. I would get projects such as change control projects or projects that were looking at troubleshooting issues in manufacture where a material was suspected of causing the issue. And I would have colleagues bringing samples to me saying, we want to make this change from maybe this supplier to another one. We know there's going to be some differences between these samples. Will they be significant enough to impact tablet quality? So I would run a series of different tests, looking at the different physical properties that I know can impact tablet quality: solid state form, particle size, surface area, particle shape, possibly bulk density, trying to answer that question. But really, I wasn't interested in these properties in and of themselves. I was trying to infer from these properties, is the powder I'm looking at going to make a good or a bad tablet? And is the change between this powder to this powder going to impact tablet quality? And the problem with this approach is that even if you understand your formulation and the role of each component, and you understand how each of these properties can impact tablet quality, and you understand the techniques used to measure them and how to interpret the results and the history of your formulation. Even if you have all of that, you're still only making an estimate. You're still only saying that this change is, high or low risk to tablet quality. And this is because you're inferring, you're not measuring what you're interested in directly. So that's where compaction analysis comes in, that instead of trying to infer from other properties how your powder will behave during compaction, you measure what you're actually interested in, you measure the compaction behavior directly. And this really simplified the type of work I was doing. For a lot of the projects that I worked on, I went from using a variety of different tests to being able to just use one to answer the questions my colleagues were coming to me with. This meant that those types of projects were now much faster, and it also meant that the data was much less complex to interpret and understand. And I'm not saying with this slide that if you have these techniques, that if you got the Gamlen, you would get rid of them. I think for some projects, you can just use the Gamlen, where it's just, is it a good or a bad choice that you're looking to make? Is it a good or a bad material that you're looking at? Is moving from this supplier to another supplier going to improve or negatively impact your formulation? But where it can get really interesting is when you start to link the results from the other tests with the compaction behavior results from the Gamlen. So say you're looking at your own APIs and you're trying to understand why this batch behaved poorly compared to another one. You can analyze their different physical properties together with the Gamlen and carry out this compaction analysis and pinpoint which properties it is that are causing that batch to behave poorly. And that's where it can get really interesting. So we're not the only ones that are recommending that people carry out compaction analysis. The United States Pharmacopoeia published chapter 1062 a few years ago, and the quote taken from it here is essentially saying that although we've been making tablets for over 100 years, we're still having the same problems we always had. We're still seeing capping and lamination issues, sticking and picking problems, and problems associated with low tablet hardness, like crumbling and friability issues and so on. So what the United States Pharmacopoeia have recommended to try and move away from these problems is that companies carry out compaction analysis. And what they recommend is that they generate the data described by the compaction triangle. And this is the compaction triangle. Some of you might be familiar with it already, but to take you through it, to generate this data, you need to compress a series of tablets at different compression pressures. You then need to measure the dimensions and the mass of those tablets to calculate their solid fraction. And then you need to break those tablets to measure their tensile strength. And to do this, and when you do this, you end up with 3 different relationships between these pieces of data. And these give you 3 ways in which to compare different powders and to evaluate different formulations or evaluate a formulation change. So you now have 3 ways of doing this to tell you how your material behaves during compaction. And this method is very much focused on the material itself. I think you'll probably see that throughout this presentation, that compaction analysis is very much a materials characterization technique. You're looking at the intrinsic compaction behavior of the material itself. If you're not familiar with the term solid fraction, it can be useful to think of it as the inverse of porosity. A tablet that has a very high solid fraction is going to have a very low level of pores. So a solid fraction of 0.9 would imply that a tablet has a porosity of 10%. And before you start compaction analysis, the only thing you need to generate, the only information you need to have about your sample to generate the compaction triangle data is the true density of the material you're working with. For a lot of excipients and well-studied APIs, you can just look this up. If that's not possible for different reasons, say you're working with a blend of materials, you can calculate it. It's an additive value, so you can, or an additive property. If you have the true density value and the proportion of each component in your blend, you can calculate it. If you don't have that, you can use an estimate. A lot of the time that can still give you useful information, particularly if you're comparing sets of data on the same type of material. But even if you don't have it, I like to point out to people that you still have this tabletability relationship to work with, because that's not impacted by the true density value of the material. And that's often the most interesting and useful piece of information out of the triangle. It does depend on exactly what you're doing, but in my experience, this is the piece of information that I use the most. And you can probably see there's a piece off to the side of the compaction triangle, where we say breaking force and compression force. And this is just to illustrate the fact that although we measure compression force, we always convert this to compression pressure to account for the tablet dimensions. And similarly, we measure breaking force, but we always convert to tensile strength to account for tablet dimensions. And this is because we don't want our data to be specific to the size and shape of the tablet that was used to generate it. By doing this, it means that the tablets that we use to generate the compaction, to carry out the compaction analysis, don't have to be the same size and shape as the one that we're using in production. You're probably familiar with hardness testing of tablets as a QC test, and the hardness value doesn't take account of size and shape, but in QC they're always comparing to the same tablets, same size and shape of tablet when they're generating that data, so it's not necessary. But here it is, because we want to get the intrinsic data of the material as opposed to something specific to that tablet size and shape. So that's the compaction triangle and what USP 1062 recommends. We also carry out a lubrication evaluation as part of our compaction analysis. This is something that isn't mentioned, well, it isn't covered by the recommendations from 1062. But of course, if you want to avoid sticking and picking, you have to have a well lubricated blend. So we've developed a method of evaluating how well lubricated the blend is. And we do this by measuring essentially how difficult it is to get the tablet out of the die after it's been compacted. When the tablet is first compacted, it will be pushed up against the base of the die, and it will be stuck to the base of the die. We first measure the force that it takes to detach the base of the tablet from the base of the die. We then measure the force that it takes to push the tablet out of the die, which is the ejection force. Now, I think it's pretty intuitive to think that if these forces are low and it's easy to get the tablet out of the die, then the tablet is well lubricated and you're not likely to have sticking and picking issues. And of course, the reverse is true. High detachment and high ejection forces indicate that you're going to have sticking and picking problems in production. So next is, how do you analyze compaction? And with our system, there's 3 steps to generating the compaction triangle data. First, you make the tablets, then you measure the tablets, then you break the tablets. 3 steps. You make the tablets using one of our D-series instruments. We offer a D1000, which can compact tablets up with a compaction load of up to 1000 kilograms. We also offer the D500, which goes up to 500 kilograms. When you carry out a typical test, we would normally say that a full test you should make 15 tablets for a full analysis, and use 5 different compaction pressures So you would make 3 tablets at each compaction pressure to give you 15 in total. This way you're looking at a profile for each of the relationships from the compaction triangle as opposed to just single points. A normal test would require typically 100 meg of sample per tablet, so you're looking at less than 2 grams of sample to carry out a full test. With our system, a test would take about half an hour. I know people have gotten it down to 15 minutes who have gotten more familiar with the system, but I think half an hour is usually about right. We offer the balance, the micrometer, and our TTA, which is a tablet tensile analyzer, which is a type of hardness tester. If you take our accessories, they all link up with our software so that the data is all automatically captured by the software and you don't have to carry out any data entry, but you are able to use your own micrometer or hardness tester or balance as you see fit. It's just a slightly different setup in the software. So that's an overview of how we analyze compaction. I'm going to show you a video now. I'm just going to open it up from the panel. So this is going to be a video of the instruments actually in action. So you can see there, that's all of the full set of instruments you need for compaction analysis on the bench. They're all quite small and portable. They don't take up much lab space. I was muted there for a second. There you just saw the dye that was filled with powder. So next we're going to tap it. So first is the compaction operation. Here you set the load you're going to apply to the powder, and then the punch moves down to compact the powder. And you can see the force displacement graph being generated on the right-hand side, and that's tracking the position of the punch and the load that it's applying to the powder. Next is getting the tablet out of the die. We've compacted it. So these are the two. This is the detachment operation, one of the things that we use to evaluate how well lubricated the blend is. And you can see the punch pushing the base of the die so that the cavity that's in the die base will move to below the tablet. So this is the detachment in action. If this requires a high force, then we know that it's not well lubricated. So now that it's finished, we now have a cavity underneath the tablet. So then when we rotate it back into place, the punch can come down and push the tablet out of the die and into the cavity. So the punch is moving down now and pushing that tablet out. So for the first operation, you set the load you apply to compact the tablet, and for the detachment and the ejection, we just measure the force that is required in order to evaluate lubrication. So we slide the die out, push the die base, and there in the cavity is our tablet. So that's the making the tablet step. Next is the measuring of the tablet step. So first you measure the mass, as I said, with our setup and our accessories. When you put the tablet on the balance, you just have to press a button in the software and it automatically captures the mass. We can set that up for several Mettler, Toledo, and Sartorius balances. So if you have a pre-existing balance, we can set up an interface with our software for most of those. This is now the micrometer. The tablet is underneath it. It's measuring the thickness of the tablet, and that's being captured by the software. And finally, we're putting the tablet into the jaws of the TTA. Similarly to a hardness tester, the jaws close on the tablet in order to measure its diameter, and then it will measure the force required to break the tablet. If you're familiar with hardness testers, as I said, it's quite similar. Our TTA is on the more sensitive side of hardness testers. Most hardness testers are meant to be used with fully formulated tablets that tend to be quite hard already, but we want people to be able to work with, say, an API by itself, which is going to make quite a soft tablet, and still be able to be sensitive enough to pick up data that is usable so that they can measure the hardness of those tablets. So this is our dashboard analysis software. As I said, it automatically captures the data, and that's the data for that first tablet that's gone into the graphs. We're going to skip ahead to 14 tablets later. So during that time, you'll be making the tablets in the same way, but after every third tablet, you would increase the force that you're applying so that you, over the course of the study, you would use 5 different forces, 3 tablets of each force to give you 15 tablets so that you have a full profile. And you'll see in the graphs that there are these red and green zones. These are to help you interpret the compaction data. Oh, I apologize. If I can, I apologize. I normally pause at the last shot. I will come back to that at the end. I'm going to move on to showing you some data next. A question I get a lot with this, with compaction analysis using our system, is if the tablets that we make don't match the size and shape of the tablets in production, and obviously our machine works at a much slower pace compared to the full-scale press, then how can we show that the data we're generating is still representative of what's going to happen in full scale? So this is some data taken from a paper that was published by Kendall Pitt at GSK. He carried out this study for 2 different formulations. He looked at a direct compression formulation and a wet granulation formulation, and he compared compaction analysis data from the Gamlen with compaction analysis data generated on tablets from their full-scale FET-A tablet press. So this slide shows the data for the direct compression formulation. On the Gamlen, our tablets are always flat-faced cylinders. We can do different sizes, we can do different diameters of cylinder, but they're always flat-faced cylinders. And here he was using 100 mg of tablet per 100 mg of the formulation per tablet, while on the full-scale tablet press, the tablets were capsule-shaped and they were 8 times larger at 800 mg. So you can see from the graphs here, we've got the tabletability and compressibility graphs. So how the strength of the tablets, as you remember from our compaction triangle, how the strength of the tablets is changing with compaction pressure, and how the solid fraction or porosity of the tablets is changing with compaction pressure. So here you can see that there is no discernible difference between the Gamlen data and the data that was generated for the tablets on the FET-A, both for the tablet strength and for the solid fraction of the tablets. So the same data, but for the wet granulation formulation. Here again, our Gamlen tablets are flat-faced cylinders with 100 mg of sample per tablet, whereas on the full scale, they're now convex-shaped tablets, and there's 350 mg of sample per tablet. And again, you can see that how the strength of the tablets is changing with compaction pressure, and how the solid fraction of the tablets is changing with compaction pressure, that there's no discernible difference between the data. So if you were working with these tablets and the Gamlen data had shown that your tensile strength was going to come out low, that you were going to have weak tablets, then you would know that when you went to production, that was going to predict what the quality of the tablets you were actually going to generate on production. Similarly, if your solid fraction had been coming out as very high, say over 0.9, you had very low porosity being calculated for your tablets on the Gamlen, then you would be concerned that when you went to production that you might have problems with capping, which is often linked to low porosity, or you might even have dissolution issues because there's not enough pores in your tablet to allow for dissolution in adequate amount of time. The next is, as you saw on the video briefly, that there are these red and green zones in the software. So in my my slide here, I've kept those red and green zones from the software. And those red and green zones are to give you guidance on what is good and bad compaction behavior. It's based off the experience of our founder, Michael Gamlen, who's been working in tableting for over 40 years, and of a group of academics and industrial professionals based in the UK who are working on a materials classification system for tableted products, or for a classification system based on how materials behave during compaction. And that's where we got these red and green zones from. They're a guideline. So obviously, if you were working with a component by itself, you might know that you're happy for it not to be hitting these green zones. But they're to give you a guide of, say, here, the top graphs are how the strength of the tablets changes with compaction pressure, which is the tabletability graph from the compaction triangle. That if you're hitting this green zone, your tablets are going to be robust and strong, but if they're not, if they're hitting the yellow zone or even the red zone, you're likely to have problems with tablets crumbling or friability issues and so on. And similarly below, the graphs on the bottom, we have ejection stress profiles. And as I said, that we use the ejection operation, the force that's required to push the tablet out of the die. We use this to evaluate how effectively the blend is lubricated, so that if the ejection stress values are high, then that means we have a poorly lubricated blend and we're likely to see sticking and picking issues. So this slide is an example of how you can use compaction analysis data to make choices, say when you're formulating, or to understand the effects of your choices. And here I have 3 different excipients of lactose, ludipress, and mannitol. And in each instance, we're comparing the behavior of these tablets when they're lubricated with either magnesium stearate or lubricated with sodium stearyl fumarate. So here, as I said, I'm only looking at how the strength of the tablet changes with compaction pressure and the ejection stress profile. The reason I'm only showing these pieces of data are because if you are looking to optimize your lubricant, those are the most interesting pieces of information for you. You want to know how the lubricant is impacting the strength of the tablet, and you also want to know, is the lubricant effective? And so that's the ejection stress profile. But also I focused on just showing you these graphs because they're both independent of the material true density value. If you don't have material true density value on hand, you still have both of these pieces of information. And I think this example shows how useful they are. So in the first example, the lactose lubricated with magnesium stearate and sodium stearyl fumarate, you can see that the magnesium stearate tablets, they're all in this green zone. All of the magnesium stearate tablets are reaching an adequate level of tablet strength, whereas the SSF, it's hitting the borderline zone, and we can see that the SSF tablets are weaker than the magnesium stearate. In the lower graph, you can see that the results are quite similar for the 2 lubricants, but you would say that the magnesium stearate, you're getting slightly lower ejection stress values for the magnesium stearate tablets. So in this instance, it's the slightly better lubricant. So everything being equal in this situation, if you were deciding between these 2 lubricants, it's likely that you would choose the magnesium stearate for it to be the lubricant of this tablet. The middle example, which is the same study but carried out with ludipress, and ludipress is a blend, a pre-blend of several different excipients. Here we're now seeing that the SSF tablets are actually stronger than the magnesium stearate tablets, but that after 300 megapascals, we get this sudden dip in the strength of the tablets. This is an example of overcompaction, where you're now hitting the tablets so hard that you're actually making them weaker, that you're introducing flaws into the tablet. And this is quite risky in production, because if you don't know this is happening, it's very easy to pass this limit and end up with very weak tablets. So even though the magnesium stearate tablets are weaker across a lot of the compaction pressures, I think that would be the safer option for the lubricant in this instance. In the lower graph, we can also see that the magnesium stearate tablets are displaying lower ejection stress values. So in this instance, the magnesium stearate is also the better lubricant. So again, I think you'd be likely to choose the magnesium stearate as your lubricant in this instance. If you knew that you really needed the extra tablet strength and you were going to be staying at low compaction pressures, then you might be happy with the SSF. But I think on the whole, you'd be likely to pick magnesium stearate. And then the final example, which is mannitol lubricated with the same two lubricants. There's no discernible difference between the data for these lubricants for mannitol. So in this case, that's still a useful result, because now you know you can choose based on another factor, based on which lubricant is more readily available, or simply which lubricant is cheaper, or any other factor you need to consider. And I think, well, if you're doing this, if you were really optimizing your lubricant choice, it's likely that you would try different percentages of these lubricants, you would try different blend times. But this is just to illustrate how easy it is to see the effects of your choices using the compaction analysis data. The next example is looking at alternative sources. So I like to include this because this is something that I was asked to do a lot. Maybe you're looking to de-risk the supply of one of your excipients, so you're not just single sourced on it, or you're looking to expand production, or you possibly you found a cheaper option for a source of one of your excipients or APIs. A compaction analysis, I mean, like I said, it takes about half an hour a sample. It can be a really quick way to find out whether it's worth pursuing a particular source as an option. You can find out very quickly if it's going to give you a similar quality to the tablet that a similar quality tablet that you currently have, or if making this change, like I said, with 2 grams of material, you can tell this instead of having to go straight into a full-scale trial, which can be quite expensive. So here, let's say you were working with MCC source C, and you were considering changing or expanding to source A or source B. Again, I've stuck with the tabletability graph, how the strength of the tablets change with the compaction pressure, and the ejection stress profile, so how effectively lubricated the material is. I am just, in these examples, it is just the MCC being tested by itself. Of course, when you add the API and so on, it's going to shift these results somewhat, but this is telling you intrinsically what are the differences between these sources. And again, because MCC provides so much of the strength in a tablet, the tabletability is an incredibly important bit of information. But MCC also, it's not, of course, not a lubricant, but because it can help with lubrication, it's also important to look at that as a factor in your choice here. So let's say we're working with source C and we've tested source A and B. You can see in the first graph that source B has a similar strength. The tablets of this MCC are similar in strength to source C, but source A, the tablets are weaker. They're not so weak that's falling into the borderline, but once you formulate this tablet and add your API, if you know that your formulation has had problems with low tablet hardness in the past, you might not want to take that risk of reducing tablet hardness even that much. Then if you look at the ejection stress graph, you can see that source A actually has the lowest ejection stress values. So this is the one that would require the least amount of lubrication. And it's less than our current source C, whereas source B is actually showing higher ejection stress values, so would require greater lubrication. So from this, I think if you were choosing between sources A and B, you would say, well, has my formulation had sticking and picking issues in the past? In that case, there's no way we can go with source B. Or has it had low hardness problems in the past? Because if that's the case, then you want to stay away from source A. So it's an example of just how easy it is to see the differences in how materials compact and how it could potentially impact the quality of your final tablets. The next slide is, I mentioned there that overcompaction can be an issue. When we think of having low tablet hardness problems, often the way people think about it is that the higher the compaction pressure that you use to make a tablet, the stronger the tablet will become. But this isn't necessarily the case. There are three types of behavior, three types of compaction behavior that you see when you increase compaction pressure. You can see the first one, type 1. This is the one that we hope for, where you're getting, as you increase the compaction pressure, the tablets are getting stronger and stronger. The payback, the increase is getting smaller and smaller, but you're still getting an increase in tablet strength as you go up in compaction pressure. Type 3 is the type that you see quite a lot, where you increase compaction pressure and this tablet strength increases up to a point, but then it levels off, where you're getting no increase in strength for your pressure. The problem type is type 2, where as you increase compaction pressure, the tablets get stronger and stronger, but only up to a point. And after that point, it falls off a cliff. You actually start weakening the tablets by introducing flaws into the tablets. And this is very important to know. I mean, it's not impossible to work with a material like this, but you need to know if this is what your formulation does before you go into production, because if operators are seeing tablets coming out with low hardness values, the reaction is often to increase compaction pressure, and then you can end up pushing over this edge and ending up with tablets weaker than before, and nobody knows why. So that's the example there of the data just showing that. So that's my last slide in the presentation. If you have any questions now, please let me know.
Thank you very much, Rebecca, for your presentation. I would like to ask the audience if there is any question they would like to ask. I already have a question here that you could answer while we check for the others. And my
yes.
question, Rebecca, is do you provide different punch and dies for this type of tests? And do they need to match the punch and dies you have in your compression machine?
So because we take account of the size and shape of the tablets, we don't need to match the ones that are being used in production. Like I said, we only make flat face cylinders, and this is partly because of the way the machine is designed, and partly because that once you start changing shape, the calculations become much more complicated with each change. And if you think about this equipment, it's very much about understanding the intrinsic compaction behavior of the material. So in that case, it's better to keep one size and shape. And if you understand how the material compacts, independent of its size and shape, then you don't need to match the size and shape that you have in production. Our calculations take account of that anyway, so there's no need to match it. We do offer different size diameters of punches and dies, but that's more about targeting different pressure ranges. That obviously, if you change the size of the area that you're applying the force through, you change the pressure. So no, you do not need to match the punch and die that you're using in production.
So basically, you offer different shapes to achieve different working ranges for pressure, correct?
Yes, I have a slide on this. So this graph shows the compaction pressures versus the applied compaction load. So if you apply this load with these different sizes of punches, what the compaction pressures you get out of it is. So the top line is a 3mm punch. So you can, the next is a 6mm punch, and down at the bottom is a 15mm punch. So you can see the pressure ranges that you get for these different sizes are massively different. So if somebody wants to target high pressures, then we recommend that they might go down to a smaller punch size, say. We do get people asking for different sizes for different reasons. For example, we've got people working in the agricultural sector who want to make big tablets for livestock. And we have people making very small tablets to inject under the skin. So we offer very small and very large punch and dies for those purposes. But the main reason people would change punch and die size is to target these different pressure ranges. And of course, there wouldn't be any point in making, say, using a 15mm punch with 100 grams of compaction load, because you wouldn't make a good tablet, it would be too weak. Whereas if you tried to use a 3mm punch with 1,000 kilogram of load, you'd probably break the punch. So we have different recommended ranges for the punch and dies.
And in what circumstances would you recommend to test each ingredient alone instead of the full formulation?
It very much depends on what you're doing. A lot of the work that I did in my previous role, I was testing individual components. You can get a lot of information out of that. Say if you were just looking to, like I said, for change control and troubleshooting issues, that you can zero in on, say you're having a problem with production, you can zero in on the exact material it is by testing individual components. Or if you're looking to change supplier, you can focus on that material itself as opposed to the full blend. But if you're building up a formulation, then obviously you need to be working with a mix at some point. You might look at each individual component to begin with, but as you build up your blend, you need to be looking at a combination of the components.
I see. I understand that there are two models for this machine. This is my last question. Could you tell us a bit more about these two models? What are the main differences?
So we have the D500 and the D1000. They are very similar, except that the D1000 goes up to 1000 kg. It can apply a load of 1000 kg, whereas the D500 can only apply 500 kg. If you are only interested in working with tablets below 5 or 6mm in size, and you don't need to target higher pressures, then the 500 is fine. The 1000 is just a bit more flexible in that you can go to those, you can make larger tablets and you can hit higher pressures. So it very much depends just on the size of tablet that you want to work with.
Very well, thank you very much. Gostava muito de agradecer a todos os participantes que estiveram connosco. Gracias, Dimitri, por haber estado con nosotros también. Te echo de menos, a ver se nos vemos pronto. E dizer a todos que estamos aqui para qualquer questão adicional. Either we or Gamlen, we will be glad to answer your further questions if you have them. Just email us either to Paralab or to Gamlen, and we will be glad to help you. Have a nice day, and hope to see you soon. Bye-bye.
Thank you.
Thank you. Bye.